All right, so my name is Devin, and we have Irina as well, and we will be talking about ABG, quality assurance, and calibration. So how the ABG machine works, there's three electrodes. The first one I'll talk about is a CO2 electrode, which is also called the Severinghas electrode. A CO2 permeable membrane made of silicon or Teflon, which allows for CO2 to diffuse through. However much CO2 can diffuse through the membrane determines the CO2 levels. So I guess essentially the CO2 and the O2 electrodes kind of work the same, and it just detects how much of the CO2 or the O2 is actually getting through the membrane. So the O2, like I said, the same thing, but it's a membrane with a platinum rod covered in polyethylene. And then the pH electrode, which is called the SANS electrode, it measures changes in voltage rather than the actual electrical current. It has four electrode terminals compared to two, like the CO2. Um, there's a glass membrane that separates these two solutions differing in pH. It measures the change in hydrogen concentration across the pH sensitive glass membrane. So those are the three electrodes that are in a ABG machine. We go forward. Types of ABG machines. So there's two main types, but there's a lot of different brands. The laboratory analyzers are the first one, and this one is what we normally see in hospitals. This is probably the one that we've been working with the most in our clinical settings. It's the one that has three electrodes that I just talked about, the pH, the CO2, and the O2, and they are implemented together into the blood gas analyzer. And it also is a microprocessor, or it's microprocessor controlled. And then there's the point of care analyzers. These ones are seen mainly in like emergency rooms, critical care units, or even outpatient clinics. They provide a quick and fast result. So if you're looking, like an emergency room, you're looking to find results quick. So this is something that you would probably see compared to a laboratory analyzer that takes a little bit longer. And then also they are portable and you can even see them at the bedside.
So there is a certain criteria that should be followed in order for our blood gases to be interpreted and analyzed correctly. First is that the blood should be collected anaerobically. What this means is that the syringe body and plunger should be tight fitting and to make sure that we expel any air bubbles which could alter our results. Next, the specimen should be adequately anticoagulated. We should use heparin syringes so that our blood does not clot, making it unusable. A sample volume of 2 to 4 milliliters is recommended in order for accurate results. The specimen should be analyzed as soon as possible for accuracy. If you cannot analyze within a short amount of time, the blood should be drawn into a glass syringe and stored in an ice water until it can be analyzed. The specimen should be adequately identified with patient name, date, and time. The FiO2 that the patient was on and when the ABG was taken should also be documented. It is also very important that the ABG be analyzed on a machine that has recently been calibrated and is appropriate so that we can assure accurate results. We always want our ABG results to be accurate, and one way that we can make sure that we are accurate is with quality control. We can break up our ABG quality control into 3 different sections. We have pre-analytical, analytical, and post-analytical. In the pre-analytical quality control, we can include patient identification, so making sure we're using the correct patient labels. As we stated previously, we want to make sure that our sampling is done correctly. So make sure that we have arterial blood and not venous blood. We want to make sure that our sample gets transported correctly and in a timely manner. For our analytical issues, we can have issues with our equipment, some of which I will explain and talk about a little bit later. Post-analytical issues can also occur, and this includes mostly communication and documentation issues, such as incorrectly interpreting results or not effectively communicating results with the rest of the team. There could be charting issues in which ABG values do not get charted correctly, causing mistakes.
And calibration. So I think that this is probably the most important component of an ABG machine. Calibration is done to ensure the machine is working properly so that we can get a precise CO2 and O2 readings, and also pH. Wrong readings can be detrimental to a patient's health. So if we're not calibrating correctly and we're not ensuring that we're staying on top of the calibration, our numbers can be off, which will then change our care plan for a patient. Calibration should be done every 8 hours according to the CLIA. So it sounds pretty frequent, but like I said, it is the most important thing to do is to try and get that calibration done as often as possible. How the calibration works is you enter a gas of high value and one of a low value. And so the analyzer will adjust in between. So 100% FiO2, for example, and then another sample of 21%, which is our lowest percent of oxygen that we can administer. And then the analyzer will be able to adjust to those settings. When calibrating an ABG analyzer, it should be done within the same temperature, atmospheric pressure, and humidity as when you'll be running the ABG. So kind of just for example, you don't want to be, not that you would, but calibrating somewhere outside or just somewhere with a different temperature compared to where you'll be running those inside the emergency room or the ICU, wherever it might be.
Some common issues that we run into with blood gas analyzers that can cause an issue with quality control. These can include electrode or sensor malfunctions. This can be caused by protein that gets deposited onto the sensors, and we can clean that off. We also want to make sure we have adequate temperature control. So a failure to maintain 37 degrees Celsius in the measuring compartment, or if we have thermometer inaccuracy, could cause our ABG results to be inaccurate. We could have improper machine calibration, which could cause inaccurate results. Mechanical problems, such as leaks in the pump, allow our samples to become contaminated. And improper sampling techniques that we talked about a little bit earlier. These include failing to anaerobically collect arterial specimens, improper storage, excessive or no anticoagulant, and bubbles in the specimen that can all cause inaccurate results. Something that we can use to assess our quality control is a Levy-Jennings chart. A Levy-Jennings chart is a graph that quality control data is plotted on to give a visual indication whether a laboratory test is working well. The way we read these charts is using a standard deviation and mean. So if you look at the chart that I have on the right, the mean is going to be the solid yellow line that is going horizontally through the middle of our chart. And the standard deviation lines are going to be above and below it. So the first line above our solid mean line, the light dotted line, is going to be +1 SD, so +1 standard deviation. And the line above that one is going to be +2 standard deviation. Going down under our mean line is going to be -1 standard deviation. And going down below that is -2 standard deviation. This is a normal Levy-Jennings chart. We know that because all of our plots on the chart are within +1 and -1 standard deviation. They're all close to the mean. So we know that they're all within the same average and they are all accurate. This next picture I have here is a picture of an abnormal Levy-Jennings chart. We know this because our plots, some of them are plotted at +2 standard deviation and some go down to -1 standard deviation. So we can see that there's a wide range of plots in the chart, meaning that our results are all inaccurate. Thank you guys for listening to our presentation. If you have any comments, questions, or concern, please let us know.